Hey, Dr. Needham.
What's up, everybody?
Not much. How are you?
I'm doing well, thank you.
Glad to hear it. Oh. Is this the right? Yeah, this is the right one. Turn my lights on in the room. How was your weekend?
Oh, probably same as yours. I didn't go anywhere.
Eh, went out to a buddy's cabin. It wasn't so bad.
Yeah. All right, how are we all doing? What's going on in your mathematical lives?
Still trying to find the right pencil.
That's a lifelong quest I've found.
Yeah. I used to have a really nice set of drafting pencils, and I miss those.
What'd you do with them?
Long story short, they got left behind.
Yeah. Story of my life.
Yeah, well, comes with the territory.
It does. All right, so let's see. Some administrative stuff first. So what do you guys get? What deadlines you got coming up?
For you, specifically?
Yeah, I don't care about that. I'm the only thing that matters.
Yeah, fair enough. I know what just passed. I don't know if we have anything coming up.
That's today. That's two.
Test 2 tonight, right? Midnight, I think, if I did it right.
Oh, yeah.
Sorry.
All right. Some people have taken it already. So far, so good. Okay.
Yeah.
What else are we going to do? Oh, so I've been wondering if or how or when to try to get a test 3 as I promised in, and I'm not sure how best to do it. So I'm still pondering, and I'm going to hold off on any final decision until I see how this test 2 goes in general. Okay. I think instead of trying to like cram a third test in, I think what I'm going to do is somehow make the final potentially count for another test if it helps you. You know?
Okay.
Again, I'm just thinking about this stuff, and I just had this weird idea before I got on here, is that maybe I will just, let's see, actually let your final exam kind of replace 2 tests or something like that. So in other words, if your final is like your highest of your test scores, it'll be a final and 2 tests or something like that. Okay.
Wow.
So like I said, don't get too excited just yet. I'm just trying to think outside the box here to give you guys the potential benefits of a third test without the hassle of having to do something extra special just before a final. Okay. But I'm thinking about it.
If we did a third test, it would essentially go over our...
I guess it would be the stuff we're starting today, the eigenvalues and eigenvectors, and then I'm hoping we can get into some of the inner product as well.
Okay. Inner products, dot products, things like that.
Yep, dot products. Okay. But we're going to have that stuff in the final, so I'm kind of testing you there. I just want to. I just worried about people who've had like 1 poor test so far and are kind of looking forward to a third test, and I don't want to like take that opportunity away from them. So I'm not sure how to do it without kind of making the rest of the people who are happy kind of busy beyond reason at the last moment or something. So I'm going to see if I can come up with some way of kind of just making that final count for another test if it helps you, and simply count for the final if it doesn't, or something like that. How's that sound?
Yes, I'm cool with that.
Okay, so I'm still thinking about it. There's a couple options. I don't know if I can implement them all in the NS Online gradebook, but I'm pretty sure I can do it in Excel if I have to.
Sure.
All right, so you guys talk to me. I thought I'd take any questions you have right now on stuff that's going to be on the test. And by the way, I did finally remember to post my homework solutions that I had sitting there, and they're up there if you want to look at them. So we'll take some time for questions, and then if you guys I'm sure we'll have time, we can start talking about eigenvalues and eigenvectors, which are fun stuff, and probably still get you out of here early. So you can go take your test if you haven't already. So off the top of your heads, any burning questions? If not, we'll move ahead and you can ask them later.
Hold on.
I'll hold. Where is everybody? Usually we have a good crew in here.
And one I had trouble on. I'm curious. We had a question. Similar to, I believe it was that one. Number 7 on homework 3.
On homework 3?
Yeah, number 7 on homework 3. Back to transformations because.
Okay.
About the columns of the columns of I3 equal are the standard basis vectors. And E1, E2 vectors E1, E2, E3 standard basis vectors. Suppose that T is a linear transformation from R3 into R2 such that T of E1 equals 6, -3 vertical. And then T of E2 equals the vector 2, 0, and T of E3 equals the vector -2, 1. Find the formula for the image of an arbitrary X vector in R3.
Okay. I was trying to look for it here so I could bring it up for everybody. Let's see. My homework 3 only goes through linear independence, so maybe I'm looking at the wrong thing. Was it online or was it one of the old-fashioned PDFs?
It was one of the old-fashioned PDFs.
Okay.
Your PDF says homework 3, but it was definitely homework 4.
Okay, yeah, that's where we, okay, yep.
Okay.
No, my fault.
Gee, thanks.
That's the one I would have found next. All right, let's see here. Oops.
Oh yeah, did you see where John Conway died?
I did. I just saw that yesterday.
Yeah, you got me back into looking at the game of life.
Yeah. For those of you who don't know, we lost a really famous mathematician the other day to the COVID virus, John Conway. All right, here we go.
A great game theorist.
Yep. Okay, so which number on this homework did you say, David? 6 or 7?
Number 7.
Number 7, got it. Okay. So share screen 2. And I will double click. Okay, so you're all looking at my homework? Or some homework? There we go. All right, so just as David said, they give us, basically, I don't know why they start out by giving us I3, but they give us the 3 standard basis vectors in R3. And they give us a linear transformation from R3 to into R2 such that they tell us where those basis vectors go. Okay. All right, so they say find a formula for the image of an arbitrary X. Okay. So basically they're asking us what that linear transformation does to an arbitrary thing in R3. Okay, so how do you want to attack it? They don't really tell us what it does geometrically, do they?
No.
So we're kind of stuck kind of figuring out, maybe if we don't know what it does geometrically, our next best bet is probably to figure out and it's never a bad bet, to figure out what the standard matrix is for that linear transformation. And once I know that, I can figure out what it does to anything, geometry or not, okay? So let's see if we can figure out what our standard matrix is. Oops, where do we go here? Okay. So I would go over here and say, my matrix A, that's a lousy equal sign, is going to be what? Okay, so this linear transformation goes from R what to R what? R3 into R2. Okay. So my standard matrix is going to be what size?
3 by 2.
It's the other one. It's always the flip.
Ah.
Because the columns always live in the output space. Okay.
Okay, so 2 by 3.
Yep, so this was going to be 2 by 3. Okay, so down here, oh, right, I know it's going to be a 2 by 3. Okay, and one big key when you have the standard matrix is what do the columns actually represent? They are the output vectors of some special inputs. What are the special inputs?
The arbitrary x vector?
Not the arbitrary, they're particular ones.
Oh, the 3 e vectors?
Exactly. They are the columns of your standard matrix are the outputs of your standard basis vectors. Okay. So my first one, 6 minus 3. My second one, 2, 0. So nothing too fancy that I'm doing here. And my third one is minus 2, 1. So that's the standard matrix of this linear transformation right here. Because they told me what it does to the standard basis vectors, I can just write that down. Okay. But once I know what my standard matrix is, I theoretically know what it does to any input. Okay. So now I can go down here, if I can fit it in here. Yeah, probably here. I can say that T of this arbitrary x1, x2, x3 is going to be what? Well, T is just a linear transformation that multiplies by this matrix. So all I do is I rewrite this matrix down and I multiply it by my what? I multiply it by that arbitrary input, x1, x2, x3. Okay. Now I'm kind of in the home stretch. All I finish up doing now is I write down what that is. Okay. So my output's going to be a vector in R2. So I'm only going to have 2 rows, and it's going to be one column. So that's a 2 by 3, and that's a 3 by 1. So I'm going to end up with a 2 by 1. And what do I end up with on top? Well, it's going to be that 6x1 plus 2x2 minus 2x3 when I do this multiplication. Okay, so I get 6x1 plus 2x2 minus 2x3. That's my top piece. And my bottom piece is minus 3x1 plus 0x2, so I don't typically write it, plus 1x3. And there you go. That's what it does to an arbitrary input. Again, the key is that they tell me what it does to my standard basis vectors in the input world. And once you know that, you know the columns of your standard matrix and you know anything you need to figure out.
Cool beans.
What else? So let me just quiz you guys while I'm looking at it. Big picture, how would you set up and solve number 8? Or number 9 now that I think about it, because they're essentially the same, but I think you get different answers. So let's just look at 8. What do you end up looking at?
Just do ax equals b.
Yeah, so you augment that a with b and see if you can solve it. Okay. So remember, linear transformations are just functions. Well, they're linear functions. But with every function, there's kind of two key questions. Here's an input, crank out the output, or here's an output, what if any input will get me there? Okay, so if they give you an input and say, what's the output? You just multiply by their matrix, because that's what a linear transformation does. If they give you an output and say, can you get there? Then you're basically seeing if you can solve some equations. So for like number 8 and 9 too, for that matter, you just kind of crank out this matrix, augmented matrix. You take A, you augment it with B, okay? And if it's consistent, then you can find an X, and any one of your answers will be your X. If it's inconsistent, then you can't do it, okay? So X is any solution to this. And like I think it was David just said, that's the same idea, just a different way of writing AX equals B. Okay. See if I fix that equal sign. Okay. Okay. All right, what else? So this test covers what? This stuff, right? Linear transformations.
Yes.
Matrix, like operations, addition, subtraction, scalar multiplication, and we don't call it division, we call it inverses, right?
Yeah.
And then what else do we have in there? Oh,
was there any arithmetic on?
Technically, it covers arithmetic, but like I said, I'm not going to just give you two matrices and say add them. I might give you two. Say, can you multiply them? If so, what's the size or something like that? But
Yeah, okay.
yeah, I just feel a little silly just giving you stuff that you can just plug into a calculator.
No, I understand.
But I expect you to be able to do it. And what else? Oh, subspaces and column space and null space and rank and nullity and all that stuff. What else?
Professor,
Yo.
are we able to check where did we did wrong on the test? Because I just finished my test and got a few questions
Oh,
wrong.
I'll probably have to. Were you able to do it on the homework? After I built that, I had to go and like build a different view for the homework for you to do that.
Yeah, if you click on the homework's name, there's a drop-down menu, and you can click on submissions and then view each of your submissions. It'll show you what you answered, and if it's correct, what the correct answer was.
Okay. So, Jessica, the answer is yes. If I remember, I will give you that
Okay.
opportunity tomorrow.
Right?
Okay, I'll write that down.
Cool. Thanks.
Okay, what else? Because I will start talking about eigenvalues.
Yeah, I'm not opposed to that.
All right, how are we doing here? Quite a few. Okay. Okay, well, if there are no more questions, I'll go ahead and start chapter 5 then. So I'm sure we can get through chapter 5. I'm hoping we can get through the first few sections of chapter 6 before the semester ends. 5, since we're kind of focusing on a, techniques and what do I need to be able to do, shouldn't take all that long. But it's cool stuff. Okay. The one thing I'm probably going to leave out, just because the nature of this semester is kind of, I like to do some stuff on kind of what eigenvalues and eigenvectors are good for. So instead, I might just point you to a video or something like that and kind of how they're used. Okay. All right. So let's do that. Let me see. All right, big day. Eigenvalues and eigenvectors. At some point, we're going to have to agree to a abbreviation for these, because I get really tired of writing all this stuff. In fact, there's also an eigenspace coming. So at some point, I just kind of call it Eigenstuff. The stuff should be clear from the context. Okay. All right. So first off, I want to give you an easy little example that kind of is an example of all this stuff. So let's take a look at, I want to take a nice small 2x2 matrix. And I'm going to multiply it by the vector 1, 3. These are not arbitrarily chosen. These are designed to do this. Okay. All right. Now I actually want to do this. All right. So what do I get? So I get a 2 vector, which is 3 and 3 is 6. And then I get minus 3 plus 21 is 18. Okay. And I just want to point out that this thing that I just got out happens to be a scalar multiple of what I put in. Only I just mistyped the wrong multiple. No, don't do that. So that thing is 6 times the vector that I plugged in. Okay. Nothing too fancy, correct? But in general, that doesn't happen. Normally, if you just pick a vector at random and multiply it by a matrix, you kind of end up getting a vector that almost seems to have no relationship to the one you started with. So in other words, what this thing is doing geometrically, I just know what it's doing to this one vector here. But if I take the vector 1, 3, the effect that this underlying transformation has on this is it simply scales this thing by a factor of 6. Okay. It kind of keeps it in the same direction, but it stretches it by a factor of 6. Okay, see what's going on? All right. Now, when I first saw this, I remember thinking, oh, that's kind of an interesting curiosity, but what potential use could this be? Okay. It turns out I couldn't have been more wrong. This stuff is all over the place. Because what we're going to see here, especially some of these videos I kind of hope to point you towards, is that these eigenvalues and eigenvectors, which I haven't actually defined, but I just gave you an example of it. So in this particular case, the 6, the scaling factor, is an eigenvalue. It's a scalar. Okay. And the 1, 3 is an eigenvector. It's not a scalar, it's a vector. Okay. So in general, this is kind of the definition. So if A is a square matrix, so again, we're back in the world where this only works for square matrices, and in a minute I'll give you an indication of why that is. Okay. And X is a vector that we do not want to be the 0 vector, because the 0 vector is kind of special in that this thing kind of always works for the 0 vector, and we kind of want to rule that out. Okay. But the condition is that a times x is equal to some scalar times x. And I have no idea why, but this scalar, they always use a Greek letter lambda. Where lambda is a scalar. Then x is called an eigenvector of A. Associated with the eigenvalue lambda. Associated. Lambda. So in the example I just did for you, this vector 1, 3 is an eigenvector associated with the eigenvalue 6. Now, if you think about it, even in the 2x2 world, not all matrices have real eigenvalues. If you're willing to work with complex numbers, then we'll see how far we get at it. I think I'd rather move on to chapter 6 than do complex eigenvalues, but it's a possibility. If you restrict yourself to real eigenvalues, not all matrices have real eigenvalues. So for example, if you think about like a rotation, if you just rotate everything by 90 degrees, no input vectors end up pointing in the same direction as their output vector because they've all been moved by 90 degrees. Okay. So eigenvalues and eigenvectors are not a given thing. When they do exist, they kind of tell you what that matrix or what that underlying linear transformation is doing to those eigenvector directions. So for example, what happens if I grab something, I'm going to stick with this same example and change one little thing. Okay. So what I want to do is instead of taking 1, 3, I want to take something in the same direction as 1, 3. So let's make it, I don't know, let's keep life easy. Let's do 2, 6. Let's see what comes out of this thing. Okay. So I believe I get 3, 2, 12. Minus 6 and 42 is 36. And that, if you'll notice, is also 6 times what I stuck in. Okay. That's because 1, 3 and 2, 6 are linearly dependent. Okay. So the important thing about an eigenvector is not so much the particular eigenvector you found, because that phenomenon of being stretched by a certain amount in that direction actually applies to the entire direction of that eigenvector. So anything that I were to grab in this direction is being stretched, in this case, by a factor of 6 by this particular linear transformation. So it's the direction that's more important than the actual vector that you end up looking at. Okay. Question so far?
No, I think good.
Okay. One of the key things that make eigenvalues and eigenvectors important, and they actually show up all over the place, is kind of a common situation where you find yourself with some model that's like a linear transformation, and you want to apply the same model year after year after year, or day after day after day. So you take some initial input, you kind of plug it into your linear transformation, and then you take that output and plug it right back in the next year, and take that output and plug it right back in the next year. So you're kind of iterating the same linear transformation over and over again. Okay. So if you're able to identify the eigenvalues and eigenvectors of whatever this linear transformation is that you're looking at, it kind of tells you what this stuff is doing geometrically. So it's telling you in this case that anything that we start out with kind of in the 1, 3 direction is being stretched by a factor of 6. Okay. If we could find that there was another kind of eigendirection or eigenvector that correspond to like a smaller eigenvalue of like 2. So in one direction, kind of components are getting stretched by 6, and another direction, components are being stretched by a factor of 2. Well, the 2 sounds like a lot until you think about the fact that as you kind of do this process over and over and over again, that 6 is just dominating that 2. So the stuff that's getting stretched by a factor of 6 is just completely overwhelming the direction that's getting stretched by a factor of 2. Okay, so in a very concrete sense, kind of the directions that correspond with your largest eigenvalues actually kind of end up telling you where things are heading in the long run as far as the outputs of your linear transformations go. I know that's a lot to throw at you at once, and I don't expect you to, follow all the heavy details right now, but that's kind of the thinking behind what the eigenvalues and eigenvectors are good for. They tell you the directions that really matter in the long run. Okay, how are we doing?
It sounds like a convergence or something.
Exactly. If you're in this situation, then your outputs kind of converge. How do I want to say it?
The transformation
kind of relativistically towards the directions that correspond to your largest eigenvalues. In fact, that is kind of how they actually use computers to actually find eigenvalues. I'm going to show you the good old-fashioned way here in a second, which is solving an equation. But when you have big matrices, you don't want to do it this way, because for a 2x2 matrix, you end up solving a second-degree polynomial. And in general, for an n by n matrix, you end up solving an n-degree polynomial. And we all know how fun n-degree polynomials are to solve. Okay, 2 I'll do, 3 if you threaten me, 4 and 5, I'll look for another job. So they use computers or calculators, I guess, will do it. And they kind of just iterate this process, and then they kind of look for which directions are kind of taken over in a very, very particular sense. Okay, hang on. I'm following along on my own little sheet here. Let me, where are we at here? Make sure I don't miss anything. Wrong one. Here we go. All right, no reason you guys need to look at that because I'm going to walk you through that. But I want to make sure I don't miss anything. Okay. All right, so we define an eigenvalue and an eigenvector. So a couple of key things about this that I want to write down, but you will believe me. Let's see. Let's do this. So let's just call this like key things about eigenvectors and eigenvalues. Key things about Eigenstuff. Everybody okay there? Okay, so one of them is that the set of vectors associated with any given eigenvalue. So you could actually have more than one eigenvector that works for a particular eigenvalue, okay? Associated with a particular eigenvalue actually forms a subspace. There's that word subspace. Of Rn, okay? So in other words, if we had two different vectors associated with an eigenvalue of 6, I guarantee you that taking any scalar multiple of any of them or scalar multiples of them and adding them back together would also do it. Okay. So on the other hand, it's kind of the opposite if we look at eigenvectors associated with different eigenvalues. So in other words, let's say I have a matrix that has an eigenvalue of 6 and an eigenvalue of 2. I know that any vectors associated with the two different values, those associated with the 6 and those associated with the 2, they can't be in the same direction. They have to be linearly independent. Okay. So vectors associated with different eigenvalues must be linearly independent. And the thinking behind it is just, you know, if I have an eigenvalue of a 2 and an eigenvalue of a 6, and I have one particular vector, I can't simultaneously be stretching it by a factor of 2 and at the same time be stretching it by a factor of 6. They're just, you know, different. The 2 and the 6 are doing different things. So if I have vectors that are having those different things being done to them, they must be in different directions. Okay. So the time has come to actually show you guys how to find these eigenvalues and eigenvectors. Unless I have time to do one more. Nah, let's do this and then we'll do some out of the book.
Before we move forward, do eigenvalues essentially, or does the A matrix that's associated with the eigenvalue act as a linear transformation that projects whatever vector that we're working with, or whatever transformation that we're working with, to I may have said this backwards, essentially to a smaller dimension, like the one that we just did. It would assume, if we used the 1, 3 as a linear transformation of 3, 1, negative 3, 7, that projects it to that line that scales to 6, or is that, I'm just...
I'm not sure I follow you, David, when you started using the projection word. So if I go back to like this one, at least I thought I could go back to this one. Oh, I was doing some wild stuff. Okay, so that linear transformation is taking that 1, 3 direction and stretching everything in it by a factor of 6. Okay. So I guess in some sense you could say, like, if you restrict your linear transformation to that particular subspace, that eigenspace right there, it's still not quite a projection. It's still a stretching.
It's not really smushing anything down.
Right. It's stretching in this case by a factor of 6. In fact, one of the things we are going to see is that I was very careful to tell you that the 0 vector cannot be an eigenvector.
Right.
Because what happens when you plug the eigenvector 0, sorry, what happens when you plug the vector 0 into any linear transformation? 0 always comes out, right?
Right.
So that's kind of like cheating. So that's not interesting because we always know that that's going to happen. So 0 is not allowed to be an eigenvector, but the scalar 0 is allowed to be an eigenvalue. So what that corresponds to, I might be getting a little ahead of us, but this will work. What that corresponds to is if there's some non-zero vector that when you multiply it by your matrix, you get out 0 times your vector, and 0 times your vector is what?
The 0.
The 0 vector, okay? So if there's some non-zero vector that is getting sent down to 0, then 0 must be an eigenvalue of that matrix. Okay, and with projections, 0 is going to be an eigenvalue all the time because we're kind of smushing stuff on top of each other. Some non-zero things are getting sent down to 0. Okay, so in one of those sentences that I just mumbled, let's go back to some key things. Okay, so if 0 is an eigenvalue, that's telling me that some non-zero vector, when I multiply by my matrix, let me actually write it down. So suppose uh, 0 is an eigenvalue of A. Then for some x not equal to 0, we don't want the 0 vector, A times x equals 0 times x, which is just the 0 vector. Because when you take anything and multiply it by the 0 scalar, you get the 0 vector. Okay. Therefore, x must be a vector that's in the null space of A. Okay. So if we have a non-zero vector in the null space of A, what do we know about the invertibility of A? So if we have a non-zero vector in the null space of A, the linear transformation can't possibly be 1-to-1 because it's taking some non-zero stuff and it's sending it to 0. Okay. And all of a sudden, those 26 properties of that invertible matrix theorem kick in and say, hey, the matrix is not invertible. No, all of its columns are not linearly dependent and all that stuff. Okay. So the takeaway is that 0 is an eigenvalue of A if and only if A is not invertible. So as far as eigenvalues go, 0 is kind of special. It's telling you if it's there, your matrix is not invertible. If it's not an eigenvalue, then your matrix is good to go. And David, to kind of tie this back with linear transformations, again, I have to sit down and figure this out, but I think geometrically, I think projections are the only ones that are not 1-to-1 and onto.
Nice.
So what is that symbol right next to, therefore x something, no A?
That's my little is an element of. My little
Okay.
epsilon.
Okay.
Oh, I know. Hang on, let's see if this changes that. There we go. There. Whew. That's a lot of work. Okay, so let's figure out how to find these things. I'm going to do a quick little derivation for you that does not take too long. And I think it is helpful if you guys can memorize this because everything about eigenvalues and eigenvectors is in here. And like I said, it's not too terribly complicated. So let's call this how to find eigenthings. Okay. So this procedure is going to tell us how to find eigenvalues and the associated eigenvectors. So remember, the starting place is that we're trying to find a non-zero vector x and a scalar lambda so that when I multiply my vector by my matrix, the net effect is just taking that vector and multiplying by my lambda. So we're trying to find a non-zero vector x and a lambda real number that will actually do this. Okay, so this is our starting point. Okay. So this derivation is not too hard. So watch. So what I'm going to do is I'm going to subtract lambda x from both sides of my equation and think of it as an equation of something equal to 0. So my next step is I kind of pull this over to the left-hand side and say, okay, I'm thinking about this as ax minus lambda x is equal to, well, I just remove the only stuff that was there, so the right-hand side must be the 0 vector. Okay. Now, what follows is like the only trick. So what I want to do on the left-hand side is I'd like to factor out that vector x. But here, I'm multiplying it by a matrix. And here, I'm multiplying it by a scalar. So if I just factor out my x, what's left in the parentheses is a minus lambda, which doesn't even make sense. I have a matrix minus a scalar. Okay. So the way I get around this is I rewrite multiplication by lambda as multiplication by lambda times the identity matrix. So in other words, I can think of this thing right here as lambda times the identity times x. Okay. So I actually introduced a matrix, although it's an easy matrix, that allows me to think about multiplying by a scalar as multiplying by a related matrix. So multiplying by 2 is the same as multiplying by the matrix that has 2's down the diagonal and 0's everywhere else. You don't believe me, try it at home. All right, so now I'm in a position where I can factor out my x on the left-hand side.
I'm sorry, that I is that's the identity matrix there in the middle?
Yep.
Okay.
That would be an identity matrix equal to the same size as A.
Yes, whatever size you need for this to make sense. Now I can factor out that vector x. Okay. So this I just kind of think of as my new matrix. New matrix. So where I stand here is I have some new matrix that depends on this lambda that I'm going to kind of go hunting for here in a second. But the situation I'm in is I'm looking for a non-zero vector x such that when I multiply it by that new matrix, I actually get the 0 vector. Okay. So I kind of need a couple things to happen at once. Since x is by assumption, I don't want to include the 0 vector. So here I have some non-zero vector that's getting multiplied by this and ending up getting to 0. Okay. So I need x to be in the null space of this a minus lambda I. So notice we need x to be in the null space, whoops, of a minus lambda I. Okay. But if we have a non-zero vector getting multiplied by some matrix and ending up at 0, what can you tell me about that new matrix? Since there's something non-zero in the null space, that new matrix must not be invertible. It can't be 1-to-1 because I'm finding some non-zero thing that gets sent to 0. Okay. So we need a minus lambda I to be non-invertible. And I'm just thinking, I'm just wondering if there's a worse way I could have phrased that, or if that was that might actually be the worst way. Okay, so we need a minus lambda I to be I'll fix it, to be singular. Remember, singular is just a fancy word for non-invertible. Okay, because we need it to have something non-zero in the null space. Now, what is probably the easiest way to check and see if a matrix is invertible or not? Keep in mind, we just did a chapter on determinants.
I was going to say that the columns are not linearly independent.
That is one thing. Yep. So that goes along with all those other things in an invertible matrix theorem. Okay.
You're looking for something.
But if you're just doing a quick down and dirty check to see, hey, is this matrix invertible or not? A determinant is usually a quick way of doing it. Okay. So if we need this thing to be singular, we'll need the determinant to be we need the determinant of A minus lambda I. If we don't want it to be invertible, we need that determinant to be 0. Okay. So this actually is going to kind of defines our approach. So what we're going to do an example here in a second. But given some matrix and we want to find its eigenvalues, we first find the values of lambda that will make the determinant of A minus lambda I equal to 0. And we're going to end up solving a polynomial here in a second. Okay. We could get multiple values, depends on, you know, the degree of our polynomial we end up doing. Okay. But then what we do is for each of those values, then we go back up here and crank out like the things in the null space of A minus lambda I. But I'm getting a little bit ahead of myself, so what I want to do is let's do a concrete example. Okay. And let's just use the one I had here before. Let's see how it goes. Okay. So example. So let's let A be that one that I started with. So we'll see how I came up with the 6 and the eigenvectors. Okay. So let's let A be that matrix right here. Okay. So what I'm going to do is I'm going to crank out A minus lambda I. Where remember, lambda is actually an unknown. It's like going to be my X or something that we're used to. Okay. So in this case, what size I do I need?
2 by 2.
It's going to be a 2 by 2. That's right. Whatever size my A is the same size the I is going to be. So what I'm going to do is I'm going to take 3, 1 minus 3, 7. I'm going to do this one in painful detail, and after this, you're going to be able to do it in your head. Minus lambda times 1, 0, 0, 1, okay, which is equal to 3, 1 minus 3, 7 minus lambda 0, 0, lambda, okay, which is equal to 3 minus lambda, 1 minus 0, minus 3, and 7 minus lambda. So that's my A minus lambda I. So what happens every single time here is I would skip the 2 steps before this, because after you do a few dozen, you'll see that when you do this A minus lambda I, the net effect is that you are just subtracting lambda off the diagonal entries of your A matrix. The others are all staying the same, and all the diagonal entries end up with a minus lambda sitting next to them. Okay. But, you know, the first couple times you do this, go through and do all these steps, and you'll never forget it. Okay, so where we stand is we're looking for values of lambda that make this a singular matrix. So in other words, what makes the determinant 0? So the next thing down here is I crank out the determinant of A minus lambda I. This is still a 2 by 2 matrix, even though I have this Greek letter floating around in it. And so I'm just going to use the formula, which says it's top left minus the bottom right, minus, whoops, I forgot my minus, times 1, okay? So now I have to FOIL this thing out. So I'm going to get lambda squared Minus 7 lambda minus 3 lambda is minus 10 lambda. So now we're back in pre-calc. It's been a while. Plus 21. And then I have plus 3. Okay. So all I'm doing is I'm prettying up this polynomial here. My polynomial is in lambda. That's my unknown. Okay. So this thing ends up being lambda squared minus 10 lambda plus 21 plus 3 is plus 24. So no matter what lambda is, that expression there gives me the determinant of a minus lambda I. And now what question do I ask myself? When is this 0? Okay. Before I do that, so some terminology wise, this is actually called your characteristic, this is called A's characteristic polynomial. A's characteristic polynomial. Okay. So I ain't done yet. Now the question I have to ask myself is, when is that polynomial equal to 0? So I need a new whiteboard here. Then let me write this down. Okay. All right, so next up, we're going to set that equal to 0 and solve it.
6 and 4.
What's that?
12 and 2.
Okay, so now solve. So I just wrote it down. So it was lambda squared minus 10 lambda plus 24 is equal to 0. Okay. All right, so how do you want to do that? The correct answer is any way that you possibly can. Okay. So let's review quadratic equations, because quadratics are second order equations. And again, it's a lambda instead of an x, but it's still just a placeholder. Okay. What are my options with quadratic equations?
Factor.
Yeah,
Factoring is actually the fastest way if it factors nicely. Okay. If it doesn't, then what?
Complete the square.
Ooh, I want to shake whoever's hand said that. Okay. I love completing the square. I don't even know if they teach it anymore. Okay.
They do.
Do they? Excellent. But that just kind of leads into the quadratic formula, right? So typically, if I can factor, I do so. If not, I get out the quadratic formula.
That one factors nicely, though.
Yeah.
This one does factor nicely, yeah. Because it's a math textbook problem, right? It's not a real life problem. Okay. So in this case, what is it? Minus 6 minus 4?
Yeah.
Okay. So I have two eigenvalues, 6 and 4, right there. We knew that 6 is one of them, right? Because that's kind of how I started out this whole shebang. Okay. So now what we do is we take turns. We let lambda equal 6, and then we go looking for non-zero things in the null space, which we actually already know how to do. So now let's set lambda equals 6 and find, let's just say, the null space of a minus 6i. Okay. So a minus 6i, and all I'm doing here, okay, is I'm going back to this thing here eventually. Here we go. Okay, so all I'm doing is I'm waiting to get signed in again. Okay, I'm going back to this matrix right here, which is my A minus lambda I for any lambda, and I'm just plugging in 6 for lambda. Or I could go back and do the whole thing from scratch. It doesn't matter. Okay, so I'm cranking out A minus 6 times lambda. So be with you in a minute. Oh, come on. You can do it. All right. Okay, so A minus 6 times lambda is...
Well, I'm not sure. You're gonna ask him.
No, I'm pretty sure it's this. Okay, which ends up being minus 3, 1, minus 3 minus, let's see, so that's minus 3, and that. Okay, so that's A minus 6 times I. Now, look weird or singular or not? How are the two rows related? They're exactly the same, right? So when I row reduce this thing, I'm going to get a row of zeros. That should not surprise me because that's how I found this entire thing. Okay, so this thing row reduces to whatever. Okay, let's see. I wonder if I should show you a shortcut or just kind of go through the way we've been doing it. So at this point, you row reduce. Yeah, let's keep doing it. Okay, so this thing row reduces down to what? 1 minus 1/3, 0, 0. Okay. So I get x1 equals 1/3 x2, and x2 equals x2. Okay. So the stuff in my null space is the set of things that look like x2 times 1/3 1. Remember, I just factored out my x2 there. Okay. So that right there is an eigenvector associated with lambda equals 6. Okay. That's not the one I had before, but the one I had before was related to that one how? It was just 3 times that. Okay, so eigenvectors are not unique. What's unique is kind of the directions associated with them. So I would say, 1/3 1, or even if I want to just kind of pretty this up, I'd multiply everything in sight by I'd scale this by a factor of 3, are eigenvectors associated with lambda equals 6. Okay. So even though I say eigenvectors, it's still in this case only that one direction. Okay. All right, now I'm not done yet because I got another eigenvalue, right? I have another eigenvalue of 4. How are we doing time-wise?
Where did you get this 1, 3 vector?
I multiplied this thing here by 3. I just scaled it by 3 just to pretty it up.
Okay, cool.
Okay. So I multiplied times 3. Okay. So again, it's not the eigenvectors that are unique, it's kind of the directions that are important. Okay, so we also have lambda equals 4. So when we plug in 4 for lambda, we get out a new a minus 4I. So now let's do lambda equals 4. So a minus 4I is equal to minus 1. So all I'm doing is I'm subtracting 4 off the diagonal entries of the matrix that I started with, and everything else stays the same. So that's a minus 4I Okay. I can look at that and tell you that's going to be singular as well, because the second row is just twice the first row, right? So this thing is going to row reduce down to 1 minus 1, 0, 0. So this tells me that x1 equals x2 and x2 equals x2. Therefore, things that look like x2 times 1, 1 are eigenvectors. So that is an eigenvector associated with the eigenvalue 4. Eigenvector associated with lambda equals 4. Okay. So let's just check this one for kicks. So let's do a times 1, 1. And what I expect to come out is just 4, 4. Okay. So this was 3, 1 minus 3, 7. Oh, sorry, I forgot my vector. Times 1, 1 equals 3 and 1 is 4, minus 3 and 7 is 4, and voila, it works, as I knew it would, because it's math. Okay, so all I did there was I just checked it. Check it. Okay, but again, any multiple of 1, 1 will also be an eigenvector associated with 4. So if I stick in 10, 10, I'm just going to get out 40, 40. So what's kind of going on geometrically with this linear transformation is I had kind of two eigendirections. So I had the 1, 3, which is kind of looking like that. I'm kind of exaggerating. Okay. And I had the 1, 1, which kind of looks like that. Okay. So it's kind of, this linear transformation is breaking my input space up into kind of these directions. Okay. And I would put like parallel things in here if I wanted to be real careful. But any vector that I would take in my input space, it's kind of breaking up into those two different directions, and they're linearly independent, so I can get anywhere I want with them. It's stretching kind of this component by the 6, I guess that's the 4. Okay, so that's lambda equals 4. And that's lambda equals 6. Okay, and then it's kind of putting them back together. So if you were to kind of put vectors, if you were to put vectors into this linear transformation that didn't happen to line up on one of these, you'd see them over the long run kind of getting pulled more and more towards that lambda equals 6 line, because that 6 is bigger. It's kind of dominating the show over time. As you take the outputs and stick them back in, that 6 is kind of taken over from that 4, and things are getting more and more in that 6 direction.
Can you say that one more time? Everything is getting closer to the 6. All the
so if I were to take like some initial input that didn't happen to line up perfectly on one of these, every time I kind of took the input and got the associated output, I would find those outputs kind of getting closer and closer and closer to that direction associated with the largest eigenvalue. It's kind of telling you where stuff is kind of getting sucked in.
Okay.
So this is essentially just a limit.
It's kind of a relative limit, because you, relatively speaking, stuff's getting closer to that 6 subspace, but you're going to have some non-zero component there as well. But yes, that's how I think about it.
Values? Okay, so it won't exceed, though, similar to a limit, it won't exceed this lambda equals 6.
No, because 6 is my biggest eigenvalue, and that's kind of the direction that matters the most, and things are kind of getting sucked in there. Unless they happen to get lined up with that 4. So if I pick something with that 4, if I pick something along there, when I plug that thing in, I'm just getting more things out in that direction. So I never really get a component in that 6 direction. But in general, if I just pick an arbitrary thing, it breaks it up into its pieces, stretches that direction by 6 and that direction by only 4. So I'm kind of getting stuff out pointing more and more in that 6 direction.
I got you.
I'll see if I can find some good animation or something online for that. I don't know if 3 Blue 1 Brown, but he probably does.
Yeah,
but he's got
some
dancing
videos
pie
here.
showing you about eigenvalues.
Weekly thing.
So does this also give us a subspace?
Yeah, so
between those
this
two?
is a subspace. The lambda equals 4. That stuff is a subspace. And the lambda equals 6 is a subspace. If I pick something in there and start adding them together, everything in there just gets stretched by a factor of 4. And the same for everything in that lambda equals 6 subspace.
I mean, between the two.
Well, in this case, it's all of my input world. Yes. So one of the things we're going to try to do in section 5.3 is we're going to try to break up the entire input world into eigenspaces corresponding to different eigenvalues. And if you can do that, then you're in a position to really kind of tell some nice things about the long-term behavior of this matrix. You can't always do it because sometimes there's a rotation involved in your linear transformation, which corresponds to complex eigenvalues. Okay. You can also deal with those if you have to. But if you can break it up into real eigenvalues and eigenspaces, then you have a real good grasp of what your thing is doing geometrically.
Cool.
What else did I want to tell you? So the characteristic polynomial, so the characteristic equation is what you get when you stick that polynomial equal to 0 on. Okay. Oh, do one thing for me. So look at my A right here, that matrix A. Quick, what's the determinant of that thing?
21.
18. No, 21.
No, 21.
24.
Careful.
24.
24.
21 minus 3 is 24. Okay. What's the product of my eigenvalues?
6
24.
times 24.
You got it. What's the sum of my my diagonal entries in this thing?
21.
Just the
Oh,
sum
the
of
sum,
the diagonals.
10. 10.
Yep. What's the sum of my eigenvalues?
10.
It's like magic. Your determinant is always the product of your eigenvalues.
So,
And we'll,
wow.
Yep. Good. So I'd mentioned that the determinant is kind of, in some sense, you think about it as like the size of a matrix, but size is kind of a funny word. It can mean different things depending on what you're doing. And one of the other common ways of measuring the size of a matrix is the size of its largest eigenvalue. All right, what else do I want to do here? There is one case. Let's see. Yeah, let's do this. This is nice and easy. So if you are in a nice enough situation, oh, let's just do one. So let's say we have a, why did this thing stop working? Ah. Oh, don't do that to me. Okay. All right, so let's say we had A equals, and I'm just going to make something up, but I'm going to make something up that's triangular. Okay. What happens when I go to find my eigenvalues? So I'm going to look at the determinant of A minus lambda I, which in this case is the determinant of the matrix 2 minus lambda, 0, 5, 3 minus lambda. Okay. And thanks to that 0 on the top right, my characteristic polynomial is just that. Okay. In fact, let me at the end go ahead and put in here minus 5 times 0 so you know what I'm doing here, but I'm just skipping the 0 part. Okay. So I'm going to set the determinant of A minus lambda I equal to 0 if and only if lambda equals 2 or 3. And 2 or 3 just happen to be what? They were my diagonal entries. So in a nice world where I have a triangular matrix, the eigenvalues are just the diagonal matrix, just the diagonal entries. So the eigenvalues of a triangular matrix, either upper or lower, are the diagonal entries. Let's see, what time is it here? 10.
Will that be the case for a triangular matrix of any size as well?
Yep, any size. And I should put that in here. For any size matrix. Okay. All right, I think we're in good shape here. Similar. Okay. So I'm wondering, do we want to find the null space of this or just move on to something else? I'll tell you what, let's just move on to something else here. Do a couple problems out of the book. Let's see if we can do, oops, too far. Where'd it go? I thought I had this going already. Oh, here we go. Let's look at so for some reason in your book, they don't actually introduce the how you find these things until 5.2, but now I've shown you how to do it. Let's take a look at, I don't know, let's just kind of start from first principle. So number one, it says, is lambda equals 2 an eigenvalue of, and they give you some matrix. They say why or why not. Well, what we could do is we could, crank out the determinant of a minus lambda and then solve for lambda and see if 2 is one of our solutions. Or we could just see if a minus 2I is a singular matrix or not. Okay, so for this guy, and this is kind of the full frontal attack way of doing it. So for this thing, I would just crank out a minus 2I is equal to, so remember all I'm doing is I'm subtracting 2 off the diagonal entries. So I get 1, 2, 3, and 6. Okay, and you tell me, is that matrix singular or does it have an inverse? Are the 2 rows related?
Yes.
Or if you want to check the determinant, do that. What's the determinant?
Determinant 0.
Determinant is 0, so that tells me this thing is singular. So this thing is an eigenvalue.
Okay.
Okay. How about 5? I would do 3, but I don't have enough room. So 5, they say, is 4, 3 minus 1 an eigenvector of, and they give us some matrix. Okay. So what I'm going to see people doing on the final exam is going through there and finding a, basically what's called what's a basis for my eigenspace and seeing if 4 minus 3, 1 is in there. But if you just kind of go back to first principles, I would just do this. I would take that matrix, 3 minus 4, 2, and I'll be with you in a minute. 7 minus 5, 4. That's a 4, believe it or not. 9, 1, 4. And I would multiply, it's becoming a pattern, and I would multiply by that 4 minus 3, 1. And I would see what comes up. So what do I get? Oh, why do I do this? 12 minus 21 is minus 9, plus 9 is 0. Middle one is minus 16, plus 15 is minus 1, plus 1 is 0. Uh-oh, I think I might know where they're heading with this thing. And the bottom one is 8 minus 12 is minus 4, plus 4 is 0. So is that some scalar of the vector that I plugged in? Yes, it is, because it's 0 times that, okay? So 4 minus 3, 1 is an eigenvector of that matrix, and it's an eigenvector associated with the eigenvalue 0, okay? So now right away, I happen to know that that matrix they gave me is a singular matrix. It's got non-trivial stuff in the null space. Okay. How about number 7? 5 minutes. Okay. So they say, is lambda equals 4 an eigenvalue of that thing? If so, find one corresponding eigenvector. So what I would do is I'm going to fit myself some room in here. So I would look at A minus 4i which is what? So all I do is I subtract 4 off my diagonal entries. So I get minus 1, 0, minus 1, 2, minus 1, minus 3, minus 3, 4, and 1. Okay. And then I would do what? Well, if I just want to see whether or not it's an eigenvalue, I would probably take a determinant, okay? But since they asked me to actually find a corresponding eigenvector, if it is an eigenvalue, I'm going to be kind of doing some row reduction, so I'm just going to go ahead and do that now, if you bear with me for a minute. All right, minus 1, 0, minus 1, 2, minus 1, minus 3, minus 3, that looks good. Oh, crap.
Thank you.
Okay, so this thing row reduces down to 1, 0, 0, 0, 1, 0, 0, 0, 1. So now tell me, is that thing an eigenvalue of the, is that thing an eigenvalue of that matrix or not? So look at that row reduced matrix. Does that tell me that I have anything non-zero in the null space, or does it only have 0 in the null space? How many free variables I got? If I think about augmenting that with 0, right. So in that case, that matrix that they gave me, okay, once I subtract 4 off once I do A minus 4 times I get a matrix that is invertible. It's got nothing non-trivial in the null space. So, wait a minute, what am I doing here? Number 7, yeah. So 4 is not an eigenvalue of it. I do not end up with a singular matrix when I do A minus 4i. So not singular. So that says, nope, it is not. Okay. If it were singular, then I would just find something in the null space, like we've been doing. I would set my equations equal to 0, pull my free variables over, and factor them out. And it being 5:18, I think this is probably a good place to stop. So where we're heading with this next is I kind of already did some of the 5.2 stuff. I'm not done with what I want to do in 5.1 and 5.2, but we're pretty close. Okay. We'll do some more examples, especially with like 3x3 matrices. They start to get a little bit more interesting. And you can have like multiple directions associated with it, one eigenvalue and stuff like that. And then in 5.3, we see that in certain circumstances, when, like if you're in R3 and your matrix is a 3x3 matrix, if you can find 3 different like eigendirections, or if every direction R3 kind of, if you can fill your input world up and break it up into nothing but eigenvectors or eigendirections, then you can really simplify your matrix in a way that gives you insight into the long-term behavior in a really slick way. But again, I will go looking for like a, if you have the book, I asked you to read kind of up here at the end of 5.1, they have a little section on like kind of iterating these processes. I think they call them dynamical systems, but I'll see if I can find a decent video on that. All right, how we doing? Time to wake up. Go have dinner.
Yes.
Doing good.
Homework for this week?
I have it somewhere. I was kind of waiting for you guys to finish with the test. If I don't post it tonight, I'll post it tomorrow.
Cool.
And it'll be like 5.1 and 5.2 stuff. Because even the stuff we haven't yet done in 5.2, I think you could probably figure out.
Okay.
But we've been through the basics.
Cool beans.
All right, we're good?
I think so.
Thanks.
Thanks, Professor.
You're welcome. Thanks for coming, folks. See
Talk
you
to you later.
Thursday.
Thursday.
Have a good night.
You too. There we go.